So I'll talk about joint work with Yochai Kaplan, Swastik Koparty, and O Meir, sitting here. And I'll include also information about, in the paper there'll be an appendix by Henning Stichtenoch about which I'll tell you some information. And the title is constant rate PCPs with sublinear query complexity. And feel free to interrupt me. So we all should be aware of the famous PCP theorem that says, and this is AS and ALMSS, which says that, I'll say it in a certain language, circuit set, the NP-complete language of satisfiable circuits over some fixed Boolean basis, has probabilistically checkable proofs with completeness 1, soundness, let's say half, proof length, which is going to be an important parameter we'll look at, n to the c for some absolute constant c, and query complexity, which equals O of 1. This is the celebrated PCP theorem. Am I going too fast? Do I need to define it? Or okay, good. And as for those who attended my talk on Thursday in Princeton, I said there that the PCP theorem is a double-edged sword. So you can use it for two things, and this was noticed very early on. One thing you could use it for, and this was shown by Feige et al., is that you can use the PCP style theorems to get complexity results. In particular, you could show all kinds of hardness of approximation of constraint satisfaction problems. And this, of course, this line of work has received a lot of attention and led to many spectacular results. Maybe the most famous of is Hastad's inapproximability results. And this is the way the PCP theorem is more used and quoted. But around the same time, BFLS noted, Babai et al., noticed that you can use PCPs also, they call them transparent proofs or holographic proofs, to get positive results, algorithmic kind of results. And in particular, what you can get is polylogarithmic verification of proofs and computations, which could be very useful. And again, this was what I spoke about on Thursday. And when focusing on hardness of approximation, people more look at things like the query structure and the resulting soundness, meaning how many queries do you make, what kind of decision predicate do you apply to it, and what is the soundness that you get for those things. That's the type of questions people look at. And of secondary importance is how long is the proof, how much time does it take to compute. You just leave them at some unspecified polynomial. Whereas in this direction, what is more important is the running time both for the prover and for the verifier. And since the prover's running time is in particular at least as long as the proof, as a proxy for this kind of question, you're very interested in the proof length. Yes, yes. Exactly. So the prover running time would be how much time, given a circuit and its proof, does the prover have to invest in order to get the PCP proof? And on the verifier side, you're also interested in, so the query complexity is again a lower bound on the running time of the prover, of the verifier, but that's not the important parameter. Again, when you're talking about verification, you want to look at how much time does it take to generate the queries, check them, and also to read them. But that's not the main issue. Okay? And again, getting back to the talk I gave on Thursday, I think we'll be seeing in coming years this side of this double-edged sword being more, brandished a bit more and complementing this kind of research. And the talk I'm talking about today certainly falls more within this range because we're talking about getting the proof length to be shorter at the expense of increasing the query complexity. Okay. So in particular, you could look at this sort of range of, let's talk about the query complexity and plot it versus the proof length for a given circuit of size n. And if we put here O of 1, the LMSS proof, and here we put n to the O of 1, the LMSS proof, this is AS plus ALMSS. Put it somewhere here, right? And we fix the soundness and the completeness. Now, previous state of the art showed that you can get it with O of 1 even down to n times polylog n. And this is my work with Madhu together with Dinur's work. Gives you a point here. But maybe let's just push it a little bit over here so we have room for what I'll put now. So this is, well, we want to go to the negative. But if you talk about O of n, so previously all you could do, and here we have n, all we had previously was this thing, which is quite trivial, because query complexity n, you can just read the full assignment. And what I want to talk about today is you can put it, well, I can push it very close here, but I'll put it somewhere here. You can get it to be n to the epsilon with O epsilon n queries. This is today. Okay, the dependence in all constants on epsilon, we can bound them. Again, this is not, so this is sort of work in progress. It could go down, but right now all constants that depend on epsilon in this talk are of the form, C epsilon equals something like epsilon to the 1 over epsilon, roughly. And this is not the final. Epsilon, oh, and this whole thing, okay, like 1 over this whole thing. So what I want to say, if the constant is less than 1, it would be epsilon to the 1 over epsilon. And if we're talking about the blow up in the proof length, it would be 1 over this whole expression. Sorry?
This work is not written.
What?
This work is not written yet.
No, I'm saying this is what we currently have, but we're still working on trying to optimize it. So this is, currently, we already know this. May go down. but just to remove. So when I say O of epsilon, I mean this sort of thing. Okay. Good. So let me state the formal. Let me state the theorem formally, and then what I'm going to do is I'll give you some details about the proof, and I won't give a lot of details because we have limited time, and a lot of it relies on pretty deep algebraic geometry. So I want to give you the sketch and tell you where the AG codes come in and what properties we need of them and how we use them. Okay, so the main theorem that we have is the following. For any epsilon, there exists C epsilon of this sort of form, such that for any n, you get a PCP, well, let's call it like this, circuit sat n. So if you're looking at the circuit sat problem restricted to length n, belongs to PCPs with, again, completeness 1, soundness greater than 0. You can take it to be half. The query complexity is n to the epsilon, and the length of the proof is C epsilon times n. And maybe you want to add that the alpha bit over which everything is taken is binary or constant size. Okay? So this is the theorem. And again, this is the first PCP theorem in which you have constant rate and constant soundness and any non-trivial query complexity, where non-trivial is little o of n. So first, constant rate with query complexity equals little o of n. Now, as a corollary, you could get that if you use standard reductions by Fisher and Pippinger from n time n to circuit sat, you get that, well, n time, let's say, call it n, belongs to the same sort of PCPs, like here. The only difference is that the length, n log n, well, C epsilon.
Maybe it's better to replace n by t.
Okay. No. For any language in n time. No.
But only with polylog t, but not with log.
Yeah. Basically, it was with add one additional log to get from n time t to circuit sat, and then you apply, let's say, Ben-Sasson, Sudan, and Dinur. So you have to add one to the log, to the poly and the log. Okay? So this is the result I want to tell you about. And in particular, the main ingredients are going to be transitive algebraic geometry codes, which require also a new form of arithmetization or a generalization of arithmetization and a new combinatorial Nullstellensatz for tensored AG codes. And I'll try to tell you a little bit about these things. So the way I want to go about it is, first of all, start with a PCP theorem that would have query complexity. First of all, OK, I'll fix. So from here on, let us fix epsilon to equal half. So we're trying to aim for query complexity that will be roughly, I mean, O of square root n for a circuit of size n. That's our goal, and you can then see how to generalize it to larger epsilon. And for starters, we'll do sort of so first thing we'll do is a standard kind of standard Reeds-Muller-based old school PCP, and then we'll see why it's not sufficiently short for our purposes, and we'll see what needs to be replaced, and then I'll tell you how we replace it and the various things that are going to emerge. Okay? Questions so far? So, as the input to our PCP, we have this circuit phi. All gates are, let's say, ands and nots, and it has fan in at most 2, and its size is n. And let's also think that the fan out is 2. We can get that by a linear size reduction. So by the way, n is number of wires. So without loss of generality, we can think that the number of gates is up to factor 2 the number of wires. And now, going back even to the work of ALMSS and so on, we're going to reduce it to sort of an algebraic problem that happens to be lying inside field cross field, and inside there's going to be some subset H cross H. And then we'll use combinatorial Nullstellensatz, or as it's been called in the PCP world, it's called sometimes zero testing, plus the local testability of Reed-Muller codes to get our final PCP. So first we'll do it in the world of Reed-Solomon, and this may sound familiar to anyone who is familiar with the PCP constructions, especially the algebraic kind. And then we'll talk about how to replace this. So circuits that are proving that a circuit is satisfiable is really a constraint satisfaction problem. Every gate has 2 inputs, and a prover has to prove that the gate functionality holds, right? If it's an AND gate, then what you see at the gate is the end of its 2 input wires. That's one thing. And the second thing is that the output gate is 1, okay? So suppose magically, and this is the second picture, suppose magically we could, I mean, not magically, we're going to do this. Suppose we could reduce this to a problem that is a constraint satisfaction problem that has the same feeling as that of circuit sat. So in particular, we're going to find some subset H of F. F is a finite field, slightly larger. And the size of H, let's think of it as being roughly square root of n, or close to that, maybe a little bit larger. So that, at least information theoretically, if we look at H cross H, which is this square here, its size is greater than n, and we have enough room to pack in a circuit. Okay. Now, suppose we could embed the circuit problem, or the constraint satisfaction problem corresponding to the circuit, into this world where we want to map the gates of phi. We want to map them to elements 8s. So x of g, y of g, that belong to H cross H. So each gate now has some element here. This is, I don't know, xg, yg. And such that the constraint associated with this gate looks at other elements inside H cross H that are, there's a constant number of them, and they are nicely structured. So what do I mean? So the constraint corresponding to G depends on value at HGYG, and two more places. Let's call them L1 of G of XG YG and L2 G XG YG. So let's say this is one input. It's lying over here. The other input is lying over there. And let's suppose that somehow we manage to get the following thing. Let's call L the set of all functions that we care about. So this will be all LAIG, where G is a gate and I is, 1 or 2. So suppose, assume that this L is a set of F linear maps, or actually affine is enough. So the degree and the size of L is at most K.
Are you sure that the function L1 can depend on G? Because then it can always be a constant, right?
Oh, wait, what I want is this thing. So the function can always depend on G. That's fine. But what I want is that if I look at the set of all functions that I need in all of this reduction, I want that set to be small. In particular, we'll take it to be less than square root n. And each one of them, so what this means is that now the circuit is much more structured. If I want to know what the value is at a certain gate in this strange world, I only need to look at two neighbors, but the set of neighborhoods that I care about is a small set. And all of these neighborhood mapping functions are linear maps. So LIG takes two field elements and gives you two other field elements. Think of it as some little 2x2 matrix, maybe plus another affine shift. So suppose you could magically do this.
The addresses, right? The L's are the addresses of the places to look at.
Exactly.
Find your predecessor.
Exactly. Exactly. Right. These are the input addresses for gate G. So as Al was pointing out, you can get this trivially if you allow the size of L to be n, right? Because you just, every input, even you can get it with two constant shifts, right? I just move to that other gate, and I just embed the circuit there inside this world. But suppose you could magically get it to be you get the circuit to be a little bit more structured. Okay. Then I want to claim that we're almost, from here we're going to have a very, from here we can get a PCP with query complexity order of square root n by sort of coding arguments and a little bit of algebra. Yeah, so there was some question? So what we'll take for the proof is going to be the low degree extension. Exactly, of the assignment. So without a PCP, what the prover gives us is just the assignment. Let's say we'll ask for the assignment to all gates of the circuit. And in the PCP world, we ask the prover to give us an assignment to, first of all, to H cross H. So this is a 0, 1 valued assignment, right? We have 0, 1. But then we ask him or her to H is contained inside F. And we can take f to be just slightly larger. Let's say the size of f, think of it as being 10 times the size of h. So we ask the prover to give us the degree 2 polynomial in x and y that interpolates these points. And its degree is going to be h in each variable. Right? So prover writes as this is not the whole proof, but it's the first step of the proof. Writes the it's called the low degree extension of the assignment to h cross h. It should be an evaluation of some function f that belongs to it's a polynomial in 2 variables, and it has degree at most size of h in each one of its 2. So its degree in x and in y should be at most the size of h. Right? Now, what should the verifier do? The first thing the verifier does, so the verifier test that f indeed is low degree. Test that degree of f is indeed less than h. And here I mean individual degree. And again, you probably know this, that one pretty good test for low degreeness would be to pick, let's say, a random point here, read everything along this row and column, and check that it's this is degree d, and this is degree d. In our case, d is size of h. There are other fancier tests, especially for low degree polynomials. You can pick a random line or a random low degree curve. You can pick you could pick a plane, but in 2 dimensions, that's really reading everything. Now notice that the query complexity here is the size of f, right, for this sort of thing. So the query complexity, at least of this part, is 2 times size of f, which for us is going to be O of square root 10. So that's okay. Yeah. Very good. That's going to be one crucial problem. Exactly. If we look at the length of this proof in bits, it is already too long. Why? Because it is of size O of n, but O of n measured in field elements. And this is precisely one of the reasons we want to get the alphabet to be smaller, and we end up with AG codes, which that's one of their properties. Good. So let me already put this remark. The size of f in bits is O of n log n, and that's too large.
Actually, the field size is the exact, it's the unique reason that we need those AG codes. Otherwise, we could have used read Muller.
Yeah. Well, starting from this point, you could have started with some other PCP construction, and then read Muller wouldn't even show up. And right, but if you follow an algebraic path, which is what we followed, then you would say, all I need to do is get this field size to be smaller, but then some complications arise, and we'll get to them in a minute. Because, but let's maybe discuss it here at this point. You could say, well, okay, let me just replace this with a constant alphabet code. Like maybe, so we know to do tensor testing of arbitrary tensor codes. Let me just take some asymptotically good error-correct binary code, exactly, and just use that for the encoding. So the testing part would work fine, but of course we need more than just testing that this is some code word, we need to test that it actually satisfies a set of constraints. And for that, a general binary code with good distance and rate would not work. At least I mean, yeah.
I'm going to explain what else the verifier is doing. So
Exactly.
see what's the point.
Good. Now the verifier really needs to check that there are n constraints and all of them should hold. And this is where arithmetization comes in. So for each g, for each gate, we can have this little constraint. Let's call it C of g. And this is the constraint that checks whether this gate is satisfied. So what does it depend on? Well, it should see the value of f at the point xg and yg. This is the value that the gate g is given. And it should see its two input wires. So it should look at the value of f at the point L1g of xg, yg. And it should look at the point So now we have one constraint, and this constraint as a polynomial, we can write it as a polynomial that vanishes if and only if the inputs line up correctly. Okay? So, and it's not hard to see that the degree of C of g is some constant. Why? Because this has only two values. Each one has only two values. It's a three-variate polynomial. It's actually a multilinear degree 3 polynomial. Now there's a small...
Actually, maybe it will be of size f, right?
Good. So I'm hiding something under the rug, which is now pointing out, and that is that as a polynomial over f, you see, if I really wanted to vanish only when the assignment f is good, I have to check that f only gives me a 0, 1 valued assignment. So I could add a bunch of constraints that just check for each one of these entries that it's 0, 1. That's a very easy constraint. It's the constraint, f squared minus f. Has only two values. I should point out that in the AG world in which we're going to move to soon, the alphabet size is going to be constant, so we can even scrap that constraint. But you could think of it as also existing. So we have a set of constraints, one per gate, that characterize when f is a good encoding, meaning it encodes when f evaluates on the set h cross h, it evaluates, sorry, it is the description of an assignment that satisfies the circuit phi. Okay. And now you can even aggregate these constraints, and you can get one big polynomial, q phi. Maybe let's put the phi up here. That will be this sort of big sum over all g. And here we have, I like to call it the sort of delta Kronecker kind of function. This is the function, or this is the polynomial that is 1 on the point xg, yg, and 0 everywhere else inside h cross h. Right? If you want to draw it, here's a point g, so you put here a 1. Everywhere else you put zeros. And there exists some low-degree polynomial of degree h in each variable that, at least on this set, h cross h, equals this selector guy. So you can have something that looks like this, and now you'll have the constraint that pertains to g. And here you will have, will depend on f of x and y. And then you will have, will also depend on f of L, I, G, x, and y for all, oops, let's make it L, for all L, I, G belonging to the set L. So the constraint polynomial basically goes over all constraints. For each constraint, it plugs in the right constraint polynomial and will pick from all possible linear mappings, will pick only those two that are relevant to that constraint, plug them in. And the point is that the degree of Q in the first two variables is less than h. And in the remaining variables that we plug into this thing, let's call them the z variables, z1 up to z size of L of Q is only constant. Right? So this Q can be computed by the verifier given phi. Here's the expression. All the verifier now needs to do, I mean, the second part of the proof, is to check that if she plugs in the value f to this constraint, get some other function, that function should vanish on all of h cross h. So, boom. The claim now is that phi is satisfiable if and only if there exists some f of degree of the right degree such that if you compose Q phi composed with f, this whole thing vanishes on h cross h. Again, if you take phi is satisfiable if and only if there is a low degree extension of a good assignment. This good assignment, when you plug it into Q in the right places over there, you should get a function that vanishes on h cross h. Notice it's not going to be the zero function because the degree of f is h in each variable. But once you compose it with Q, its degree will be, I don't know, 3 times h. So the fact that it vanishes on a set of size h cross h does not necessarily imply that it's the zero function. But the picture we should get is, so if this is f cross f, and here we have h cross h, so let's call our function maybe f hat of f. That's the composition of Q phi with f. If we look at f hat of f, we should have 0 here, and then outside, I don't know what. But the degree of f hat of f is also not too large, right? Because it is at most the degree of f times some constant. Shall we see why? F hat of f, how was it obtained? You plug f into this guy. So when you do a linear transformation on the inputs of f, the degree of f doesn't increase. Then you plug it into C of g. C of g, each C of g is constant degree, let's say degree 3. So what comes out of each one of these C of g's is something of degree 3 times h. And now you multiply it by something of degree h. So you'll get that the total degree of this thing is 4h in each one of its 2 variables. So the degree of f hat f is at most 4h. And now we reach the zero testing part, which is how do we know that a low degree polynomial vanishes on a set of the form h cross h? And again, in the PCP literature, this would be called zero testing, though as we showed in our work with Sudan, it's equivalent to the combinatorial Nullstellensatz of Alon. And here's a nice little statement. So if you have some function, let's say h, that belongs to, it is at most degree d, it vanishes on h cross h if and only if there exist h1, h2 that actually have slightly lower degree, would be less than degree d minus size of h, such that you can write h of xy as product alpha in h x minus alpha times h1 of xy plus the product of alpha in h, sorry, this should be y minus alpha times h2 of xy. And this is Alon's combinatorial Nullstellensatz. So why is it important for PCPs? Because the whole point was to verify that all of the constraints vanish, which means that you have this polynomial and you need to check that it vanishes on a set of the form h cross h. And here is a reduction of that problem to just testing low degreeness. Why? Because to prove that a function vanishes on h cross h, sorry, that this h vanishes on h cross h, the verifier could ask the prover to supply this and this. And now what the verifier, so this is the full proof. So what does the proof look like? What does the PCP proof look like? First of all, there's going to be f. And then there's also going to be, supposed to be f hat of f. This thing is supposed to be 0 here. And then there's supposed to be h1. And there's supposed to be h2. And what the verifier does, first of all, it checks low degreeness of each one of these things. Then, so the tests are 1, low degree test of each one of these functions. The second thing is consistency. That's sort of easy to check. So for instance, if I pick a certain point here, xy, I'm expecting to see here f hat of f at the point xy. I have this expression, so I can just compute it based on all the values that I need to read from this table. And that's a small number because L is a small number. The set of linear maps that I need to, that the value here depends on is small. So that's consistency. I can also check consistency of this guy with these two functions using the combinatorial Nullstellensatz. And then the third thing I need to check, well, is zero testing. Actually, consistency will refer to this part. And zero testing refers to checking that this thing is 0 by means of checking that it is corresponds to this expression. So if I call this, let's say, 1 star, so zero testing is this 1 star thing.
That's another consistency.
It's another consistency check, right? And if I call this thing double star, then this is the consistency check. So now let's go back to the original problem that Andy pointed out. We have too large an encoding because each field element is log n bits. So the overall encoding length is n log n measured in bits. Now let's see, what could we do? one thing we could try to do, and this is what has been done when people constructed constant rate locally decodable codes in the works of Koparty, Saraf, and Yechanin, and locally testable codes with the same parameters. This is the work of Widerman. What you could do is pack. So you could say, let me take many bits, pack them into one field element, and then encode it. So when you talk about error-correcting codes, this is completely legitimate and possible, and it will work. But if we try to do it with our case and just pack many bits into one field element, what would the problem be? Right, the bits in our world have a meaning, right? They are values on wires, and we need to check things that correspond to these bits. So if we pack them all together into chunks of size log n, our tests will suddenly have to have much higher degree because we would have to sort of unpack the bits and base our tests on individual bits of them. So packing is not an option. Okay, it would just blow up the degree of the constraints, or we would have to unpack and pay this log n factor later.
It's essentially like that it will blow up degree, or it's just the trivial things that work.
Sorry?
Is it essential, or there is just trivial things that it works here?
No, I can't prove that there is no way to pack that won't blow up degree.
But you can prove it if, you know, for the predicate CG, maybe you can do other encodings. But the predicate G that just makes test consistency of bits. If the values of these bits are bits, to extract them out of field elements, you need the size of the field. I mean, any Boolean function on a field takes a field size as the key.
Anyway, I think that Klim's comment is important because, I mean, what Eli said, I mean, it's a serious obstacle that we don't know how to bypass, but, I mean, maybe it is possible to do packing somehow, we just don't know how to do it.
Yeah. Yeah, so sounds hard, but yeah, and as Avi pointed out, if you try to do it just in the natural way, you can prove that it won't work, that it will require higher degree.
Natural or unnatural, if there is a function on a field that's supposed to give you only two values, it's that really high. That maybe you don't have to check the value, you check values differently. But
Exactly.
the natural or unnatural from a field with two values, whatever I do.
Right, but the hope could be that maybe most of the tests you only need to test things like you know, equality, and it doesn't matter what the bits are, and then you unpack and don't pay a lot for it. Sounds hard, but okay. So by the way, when should I end?
20 minutes.
20 minutes, okay. So packing won't do the job for us. And the other option that we already discussed was, well, let's try to just use a good error correcting code over the binary field. And then the problem, and this is where the automorphisms are going to come in. The problem is the following. You see a constraint. Let's look at this constraint polynomial. A constraint really depends on the value of f at other points. And the way we did it in the world of polynomials was to use linear maps. So we query f at a point xy, and we query f at a point L of xy. Now, why did we use L and require that L be linear? The reason is that when you compose a low-degree polynomial with a linear function, you get a polynomial of the same degree. Degree doesn't go up. Okay? Now, why do we care about degree? Let the degree go up. The problem with degree going up is that the degree, at least in the world of polynomials, is tightly related to the distance of the code. So if we would have allowed the degree to go up, the distance of the resulting code, for instance, if we compose f, which is of degree d, with some other mapping that is a high degree polynomial, the resulting function would have high degree. And what it would mean is that this little creature, f hat of f, would not have low degree. If it does not have low degree, it could have very small distance. And that's very bad for PCP purposes. Why? Because the prover, and this is the original hard problem with verifying circuits. What if the prover wants to cheat by giving an assignment that is completely legitimate on all but one gate? That would correspond in the coding world to having, this would be some assignment of zeros and ones, so that when you compose it with the constraint checking polynomial, you'll have somewhere 1 out of n values will be 1. Everywhere else it would be 0. Now the question is, will you detect this? So of course, if you query all of these endpoints, you will detect it. But the whole point of using a PCP is to get away from that need to check everything. So if the code has large distance, morally, and this is actually formally true, if you have a 1 here, you're going to have a whole lot of non-zeros everywhere. And this will cause a lot of inconsistencies, and your probability of finding out this error will be constant as opposed to 1 over n. So it all hinges around the fact that this creature, the composition of the constraint with the original encoding of the assignment, is a code with good distance. And if we would just throw low-degree polynomials and take some other good code, we would lose this fact. So what do we need? And now let's get down, and this is why we really go for AG codes. What do we need? We need a way to compose constraints with the code word and actually even permute the code word, right? Because we're going to query not just f at xy, we're going to query it at points of the form L of xy. So we need some ability, some flexibility to take a query a code word at one point, query it at another point, multiply the two, and argue that the resulting thing is low degree. Okay? Is a good code word, has good distance.
And I have a question. Do you get LDPC code which is transitive and with a good distance and rate? Is it true?
Well, if you by LDBC you allow me query complexity square root, then you get, but you would if you just wanted coding results, you could take Widerman's work, which would be much better, and that problem is already solved.
No, actually, you could do testing just with such an LDPC, just as you could do any testing of tensor code.
Right.
The thing is that we have transitive tensor, we have transitive LDPC codes, but the key thing is the multiplication. In order to solve this, to replace the linear maps, we could use any transitive code. But the thing is that there is another ingredient, which is the multiplication, the polynomial CG. What it does is to multiply what is the letter used for the proof?
The F.
F. It multiplies F with F composed with its automorphisms, and it multiplies those two, and it relies on the fact that the result of the multiplication is a good code. And so more abstractly, you need a code that has the property that if you multiply two code words, you still get something that is a code word of some good code. And we only know how to achieve this property with polynomials and with AG codes.
Okay, so let us now say what are the properties that we need of a code that can be used in a PCP construction. And again, this is not a necessary condition, though I don't know, I think morally it's not far from it, but it certainly is a sufficient one. So we need a code that is, first of all, good in the classical sense, meaning it has good rate and good distance. So these would be called asymptotically good. We need it to be over a constant size alphabet. The reason is we don't want to pay packing. We do not know how to pack bits. And we don't want to pay the price of taking a bit to a message element of the code. Okay, so we really need constant size alphabet with two properties, additional properties. One is the multiplication property. And that means the following thing. If you look at C times C, what is that? You take the span of any f times f prime of x. So this would be, right. Oh, I should say that we think of our codes, and this is a useful way to think of them in our context, as functions that go from some set to a finite field. So the multiplication of the code multiplication means you take a code word, which is a function, you take another code word, and you multiply them coordinate-wise, and you take the span of all of that. Now, if this looks, sorry, it belongs to C. If this looks mysterious, this is just what the analog of, if you start with degree D Reed-Solomon or degree D polynomials, and you allow multiplication of any two polynomials, you'll get degree 2D Reed-Solomon, or polynomials of degree 2D, and that's the exact generalization that we need. So what we want by the multiplication property, we want C times C to have good distance. That's what we want. And again, if you just take take a random LDPC code, well, I guess one, by counting argument, would be able to prove that even a random LDPC code would probably have the multiplication property. Maybe, I don't know, sort of. OK, so I take that back, because actually the multiplication now is something a bit strange, at least over binary, no? That would just be the and. Oh, but when you go to the linear span.
The thing is that the dimension would be much larger. The dimension of the span would be much larger. So
right. OK, so I even take that back. Not even a random code, it's not clear that you'll get multiplication property, and that's something we definitely need. And we actually need it not just twice, but a constant number of times. And the second one, and this is where the automorphisms come in, we need it to be transitive. Or this could probably, or maybe could be relaxed a little bit. So we need the code to be transitive. What does that mean? We want that for every x and y belonging to the domain of the code, there exists some permutation of D that, first of all, sends x to y. And most importantly, if you look at f composed with pi, meaning you take this thing belongs to C for any f in the code. If you take a code word, and instead of looking at f of x, you look at f of pi of x, and write down that table, that is a code word. Now, in the case of Reed-Solomon, what would play pi? Or in the case of low-degree polynomials, what could play pi? Affine transformations. Right, affine transformations. If you take a low-degree polynomial and you have 2 points, and you want to send one to the other, take an affine transformation that sends them. And if you compose f with that affine transformation, you started with degree D, you still have degree D. OK. And actually, this is all we need. Well, it's a lot to ask for, I must say, but because you want codes that are asymptotically good. But I'm saying these are the algebraic or coding algebraic properties that we need in order to get the PCP rate or length of the proof down.
And you need something about door, right?
No? Oh, it needs to be a linear code.
No, you need it will be testable.
OK, so what the testing we can take care of in a sort of, that's not trivial, but the testing can be taken, OK, you know what? Good point. OK, yeah. So how do we deal with testing? Right, Klim is making a very good point here. You would also need, I mean, OK, suppose you had such codes. So how would you replace or augment this sort of PCP with PCPs based here? You would say, well, first of all, let's encode the assignment by one of these codes. OK. Now, the first thing would be to test it. Oh, but are these codes locally testable? That's Klim's question. So what we actually do is the following. We look at tensors of tensor codes of codes from this family. And now with tensor codes, there's already a sequence of works that studies the local testability properties of tensoring. And in particular, we use some very powerful recent results of Michael Widerman to show that, and also of O, previous results, that you can apply, just by the fact that you take the tensor of good codes of this form, you can solve the testability aspect of it. And the way you'll solve the testability aspect is you'll read a row and a column and check that they belong to the code.
Yes, but this where your square root n comes in, right?
That's where your square root. Well, it comes more than one place.
Square root and log n. That's not the problem. The size has to be n.
But you don't want to pay even square root. Okay, you could. Okay, we pay actually square root n. You could afford square root n log n, right? But it's good to pay square root n. Your price of square root n comes from two different sources. One is okay. The real place it comes in is from these the analog of these automorphisms. That's where you really pay a square root n, and that seems pretty. Okay, I think that there is some sort of a lower bound hiding in here, at least for a set of PCP techniques, which is there's this whole problem of taking a circuit and mapping it into some structured circuit or some structured world.
It's no problem to say that you require also testability, but something it makes sense. It testability, the way that the fact that you take care of it within whatever.
Okay,
I mean, that you have to solve all these problems.
I agree.
So
Well, the reason maybe we put the cut here is because, as I mentioned, there's an appendix by Henning Stichtenhoff, and this is what he gives us. So I should say that he already had a previous result from 2006 that gave such codes, but for the fact that he only showed that for asymptotically large n, such a code exists. But the spacing between two consecutive block lengths for which you had such marvelous codes was too big for our results.
I wonder if, for example, you have this code, but which has some stability property. Can you translate this stability property into tensors to some better parameters, or it's impossible?
No, right now. And that's what I hinted at, that I think there's also some hiding lower bound, at least for a large range of techniques. And the thing is this, forget about, suppose this was locally testable with query complexity 3, okay? So you would still need to check this guy. And now the question is, can you pack general circuits into circuits or structures of size O of n? Okay, so it's like a constant rate reduction to a structured problem where you only use, let's say, linear functions or automorphisms of this sort. And then the question is, what is the degree of the resulting constraint problem that you have? And as long as you're going to use any sort of universal routing techniques, then you will need n to the epsilon queries if you pack it into constant rate. So it's not that the testability, okay, getting the testability to O of 1 is a great open problem, but that won't solve the bigger and probably inherent problem in all of the PCP constructions that at least exist today, which is that hiding within, you are restructuring a constraint satisfaction problem by putting it on some universal structure, where universal means that you can map any permutation or any graph onto it. And then your query complexity is going to be at least the degree of the graph into which you embed it. And all PCPs that exist use that thing in particular. And for that kind of construction, you have information theoretic bounds that will tell you that if you're using it an O of n reduction, you will pay n to the epsilon. So that seems like a harder problem to solve.
you're going to explain the code?
I'm not going to explain the codes because that would involve a lot of algebraic geometry. They are what's known as, they are obtained from the Garcia-Stichtenhoff towers, which have, so some things in these codes are very pleasant and easy to explain, but the important things are sort of mysterious, in particular bounds on the genus. I mean, the number of points in their block length is easy. The genus, which is really the only thing you need in order to explain things like distance and rate and the relation between them, is somewhat mysterious, at least to me. And that's just for getting the codes. The automorphisms are,
So wait,
okay.
the table that you drew with H and F, what replaces it? The field is of finite size, so you take an extra.
Okay, good. So let me then explain just what will the codes look like. So instead of taking F to belong to read Solomon, or meaning, you know, F to be an evaluation that goes from a field to a field, let's say less than the size of H, right? This is the code C that we took. What we replace it with is some algebraic geometry code. So what does it look like? It's some AG code. And it is a set of functions that go from some D. D itself is contained in F to the M. This is something like F, let's say F9, or maybe let's take it F16. So this is the finite field with 16 elements. M goes to, you know, M is pretty large. You pick a very careful set of points there that happen to lie in some curve. Curve is an irreducible one-dimensional variety inside F to the M. And this curve happens to have many rational points. So it happens to have, so a curve is just, you have M variables, and you have M-1 equations sort of in general position, and you're looking at all solutions to them. And these curves have a lot of magical properties. One of them is that the curve has many, many points that lie in the base field. So there are many, many tuples of M tuples of F16 that actually are solutions to those M-1 equations, okay? And that's why these codes have good block length. So you take D to be the set of all these solutions, and there are many of them, and F maps them to FQ. So basically F, you can think of it, F really is F of x1 up to xm. It is a low degree polynomial, but the big difference is you don't evaluate it on all of F16 to the M. You evaluate it on a very carefully chosen set of points. Like if it would have been in 2 dimensions, you know, there was some curve of points, and only on these points you evaluate your bivariate polynomial. That's what these Fs look like. And now, the other magic, so there are many magic properties. First of all, that there are many such Fs, and furthermore, the distance is very large. And the third thing, which comes for free if you're using an AG code or a GOPA code, is you have already the multiplication property, because these Fs are low degree, and if you take 2 low degree things and multiply them, it's still low degree. Okay, so that you get sort of for free. The other mysterious.
The product is evaluated still on the same curve.
What?
The product is evaluated.
Yes, the product you evaluate on the same curve, and you actually, the degrees double.
The whole code is defined by a single curve.
What?
The whole code is defined by a single curve. You're just evaluating different polynomials all on that.
Exactly. Exactly. There's a set of points, and this set of points has an algebraic meaning. It comes from, it's the set of points that lie on a curve, and you evaluate only on those points. So in the end, you just have functions, low-degree polynomials evaluated on a carefully chosen set of points. If you care to hear this, even this set of points has a very simple structure to describe. It's what's called a tower. So the curve itself is a tower, meaning you take one function over 2 variables, and you just repeat it on consecutive. You have some, yes, you have some h on xi and xi minus 1, and you apply it m times. That's how you get m-1 equations on m variables. And even these equations have a very simple form and can be, I guess that's the reason. You know, if you just pick random equations, you'll get a curve, but analyzing its properties is way beyond what anyone can do. So these sort of things, these towers, are actually accessible, and that's what Garcia and Stichtenhoff That's one of their major contributions, showing here's a way to actually present you with code that gets.
I think random equations will not give you a good error correcting code.
Because they won't give you a good error correcting code because they won't have a lot of points.
They will not have a lot of points. They will have pretty.
No, but there'll be a good variety, right? If you pick
No,
n minus
because
1.
high genus, so it will give you pretty bad parameters.
I agree. I agree.
And the reason why you need all this tower is because you don't want to take alphabet size to be large. So instead of taking f q and go q to infinity, then you just take f16 to the n, take n to infinity, and this gives you alphabet to be small. So here is from d to f16. It's not q.
Right, Q is 16. I agree. The additional magic ingredient that, again, Stichtanoch provides us here for all sizes D is the fact that you can get transitivity, which relates to or arises from the automorphisms of some extension algebraic function field over a base field. No, it's definitely not two transitive. It's one transitive. It's probably, I would guess that it cannot be two transitive for that sort of.
Only two transits there is
Not clear. I think over finite fields, it's not. No. Okay, we can take this offline.
And they are linear maps. They are automorphisms.
Well, what?
You need some property like you're composing F with an automorphism.
Yes, so I guess you're right. They are linear maps, but yeah, there's. I want to say that it's not a linear space of automorphisms. So the automorphisms themselves are linear maps, but you cannot take two such linear maps and add them up. It's not all linear maps.
But you don't need all.
Right.
You don't just need them to be rich enough for the embedding.
Right.
And the embedding, where do you get from using this automorphism? You have to deal
Which,
with
sorry, which embedding?
of the circuit into the basically here to the curve, right? You have to place the gates on this.
Okay, so once you have transitivity, you can, it means that you can use, okay, we embed things on the hypergrid or hypercube, and this also relies on works of I think, Dinur and Meir, but goes back, the way you embed it actually goes back to routing from the 60s. The fact that you can route any permutation on a grid with constant dilation.
You don't use the log n factor there also when you do the.
Because the degree is very large. Usually shuffle exchanges with a constant degree or small degree, then use the log n, right? Or De Bruyne of these guys.
Oh, I see.
Now you're using very high degree.
You can use the
Exactly.
epsilon is just
Exactly.
1 by epsilon.
Exactly. And this is the bottleneck that I was referring to, that even if you have local testability, the fact that you need some shuffle exchange or universal graph, and you want it to be constant, the number of vertices is constant in the circuit size, and still be able to shuffle anything to anything, that will lead to degree and to the epsilon. So I guess my time is up. And I just want to say that I think the complexity applications of AG codes with interesting automorphism groups is a very interesting direction. So you probably know that the whole study of the automorphisms of linear codes is something that has been gaining a lot of attention in recent years. There are works by Kaufman and Wigderson and Kaufman and Lubotsky. And there is a line of works that started with the work of Kaufman and Sudan that looks at affine invariance. And very recently, so this is going to be in the upcoming stock, in work with Ariel Gabizon, Yochai Kaplan, Swastik, Koparty, and Subangi Saraf, we also show how the automorphisms of, again, of of AG codes can be used to get better locally correctable codes in a certain range of parameters that wasn't yet known. And here the transitivity of AG codes really is crucial for getting constant rate PCPs. And I think there's a lot more to understand there in the way. First of all, there are two things I would like to see done. One is to get a CS-friendly presentation of algebraic geometry codes. And in particular, the one mysterious thing is genus. And like, how does it correspond to the, or how do you actually get it in ways that would be good for us? But also just the applications of these codes to complexity, I think, is a new and interesting direction that we should all explore more. Thanks.
You don't understand something about this word.
I have just wanted to comment. First of all, Minelli is being too modest. There are a few more contributions here. So there is so even if you have such codes, you also need to be able to somehow generalize the combinatorial Nullstellensatz to use this code. This is a very nice
So it's a statement of the same form. It's a statement of the same form. So you take functions and curves and
Yeah, but there are disclaimers because as opposed to curves of genus 0, where you're crucially using the fact that a function vanishes, even in the univariate world, a function vanishes on a set if and only if it can be divided by this guy. You would like to say the AG analog. You would like to say a function, suppose you have H a subset of D. You would like to say a function vanishes on H if and only if some algebraic characterization happens. There's some Xi that divides it. Well, it turns out to hold, but you need additional auxiliary functions. The reason is this. It could be that because these are not, this is a very weird set of points, it could be that if you want a function to vanish on H, first of all, it will vanish with higher multiplicity on some points. And second of all, it would come with some auxiliary zeros always attached to it. And so just dividing, saying, oh, so in particular, you won't have in the space of legitimate functions, you won't have a simple characterization just in this form. I mean, this is the simple characterization. It's one function that clearly divides it. You don't have that, but luckily you can work around it. So basically, you would say f vanishes on H, if and only if, first of all, you can compute an auxiliary function. You multiply f by that function. That would take care of multiplicities and zeros and whatnot. That thing is divisible. So you would have two auxiliary functions as opposed to just one. And this thing arises when the genus is greater than 0, which is exactly the case we need.
Enough points, it should be easy, right?
What?
If you have enough points, you have a simple function just vanishes on your set F.
Even if, no, what do you mean? If you have enough, no, if the
Space of
if the divisor is large enough with respect to the genus, I think you still won't be guaranteed that every H of small size is what we call a splitting set. This is a splitting set, meaning, so I'm not sure you can show that. It's true that you need H to be sufficiently, okay, you need the divisor to be sufficiently large with respect to the genus for our thing to work. Our thing does require two auxiliary functions as opposed to one, and I'm not sure. One could say that if the genus is large enough, sorry, if the divisor is large enough with respect to the genus, you will have lots of sets H that are good, that are splitting. And for PCP purposes, it's sufficient to have even one of them. So you could work that way. But as long as we're doing it, we might as well generalize for other purposes and show that any set H, you can get the analog of combinatorial Nullstellensatz, but you'll have additional requirements. Yeah, thanks. Thanks all. I guess I didn't want to talk at all about the AG part, which is, I mean, I'm sure you already see this. It's highly non-trivial. And yeah, the theoretical CS community should get a better understanding on our terms of what the basic AG parameters mean to us. And I think that's a project for a lot of people. And Could take a while.
I'm not sure if you erased it, but you had this set L, capital L of linear functions relating
Mhm.
the g's to their predecessors, the locations of their
Right.
predecessors, and it had this, it was non-trivially small.
Right.
Talk about how you guaranteed that.
So, okay, I didn't talk, that's another thing that, you know, I was modest about. And again, right, we use techniques, as I said, of Dinur and Meir that rely on routing that goes back to, you know, even the 60s. But basically, once you work with this product set of psi square root n by square root n, you use the hypergrid. So the vertices can have as their neighbors anything on the same row or on the same column. And then you can, with constant rate, you can map any circuit using that. Use 3 or 4 of them in slightly larger size, but that's the idea. And you can see how transitivity comes in, because you're really only using the fact that if you fix all variables by 1, but 1, you can go to any other guy there. So in the world of the transitive AG codes, we use the fact that we have tensors of AG codes, and we say fix all variables but 1, and you have some automorphism that will send you from that point to any other point in the same axis parallel row.
So it basically looks like a shuffle exchange.
Yes. Yes, or on a hypercube or hypergrid. Yes, that part is exactly routing on a hypergrid.